It's time for a project, one involving plastic foliage from pound shops, lots and lots of wire, lots of LEDs and mains voltage, and the potential for electric shock, but that's a minor technicality. So I've made plenty of these things before. It's just something I like making. It's clusters of LEDs, and the idea is that I'm going to have a hub with the cluster of LEDs and little bits of foliage stuck in, so you end up with some sort of floral display with LEDs through it. The nice thing is that it's going to draw very little power, and it's going to have swappable LEDs. The slight downside of that is that the connectors I'm putting them in are these little standard Molex style connectors. I say Molex, it's a generic style that is made by Molex, but also by other brands. And the nice thing about them is that you can just stuff LEDs into the end of these, and it means that you can basically swap. I was going to say hot swap. But as the open circuit voltage in this, it's effectively going to be either a capacitive dropper or a resistive dropper. It's going to be quite a high voltage. I wouldn't recommend actually changing them live. This also gives me an opportunity to try out these connector shells and contacts that I got from eBay. Because it turns out this, what I often describe as the mini Molex, does actually have a number on eBay that pulls it up. The key number, should I say, is KF 2510-2P. The 2P must mean 2-pole. And what you get is you get a bandoliered strip of the contacts. This is a common way they provide these. It's really supplied in this style to aid manufacturing, also for the machines, so that when the machines actually put the crimps on, you can just feed these in, and as it ratchets it forward, it can then crimp them and sever the crimp off at the same time. When you want to separate these crimps off, just get a pair of long nose pliers, grip the strip at the side here, and then flex the crimps backwards and forwards a couple of times, and they'll drop off. It's quite easy getting them off. Crimping the crimps is a thing. You see, the best tool I've found is this one from Rapid Electronics in the UK. And this, the crimping position I use is the one that says AWG 24 to 30. And this does a really good job of crimping these crimps. However, I've been trying other ones. I've been trying another tool from eBay, which, what's this one labelled as? It just says 0.25. Not sure. And then 0.5, then 1 millimetre. I've tried this one, but I've not had as much luck with it. It crimps them, but when you actually snap it into the shell and then hold the shell and drag the wire, it's likely to pull the wire out the shell. The other tool that has worked, and I'll just put this one out of the way. Oh, this one, did I say the number? This one was SN-28B. Seems to be commonly used for these, but I'm not sure it's the perfect tool for it. The other tool I have had success with is the unusually expensive for what it is Japanese one. Connector pliers. I think this is Engineer brand, PA-09. And these are just, when you see the price of them, you'll be thinking, why are they so expensive? But these are fairly well engineered, I suppose. And these do work, but you have to crimp two bits in two sections. If I show you, I'll just doodle it, in fact. I shall doodle it, that's the best bit. I shall doodle it in amongst the other doodles that I've already done, because I've been drawing down schematic details here of how I'm going to do this. If you look at these crimps, you'll see that at the end there's a sort of bit comes up like that, and then there's another bit that comes up that's slightly smaller, and then it goes on to the actual spring-loaded shell. So this bit goes down like that, and then it goes up to that little flap again, and onwards. And the idea is that when you lay a cable in to this, from the side it will look like this. It will have this sort of little tabs sticking up like that, and then the smaller tabs sticking up. And when you lay a cable into that, you put the insulation of the cable in here, and then the stripped core goes in there. And when you actually crimp it down, it's quite important to put it in these tools the correct way, because if you look at the crimping tool itself, you'll see at the top of it looks like this. It's got this sort of little McDonald's M type shape, and the other side, the crimping tool that comes up and pushes it into that, is shaped like a little anvil that just pushes it in. And when this is pushed in, it doesn't just mash those tabs over like that, it actually folds them round. The shape of that is such that as they go up, it curls them round onto the wire in the middle and bites into it. And that's quite important. It's what provides a good tight strain leaf and a good tight connection. So I found for these particular crimps, the best position for the cable restraint, the one at the very end, is 1.9mm, and then you can do the conductor bit with 1.6mm. Other things worthy of note in this project are that I'm using solid core wire, and technically speaking that's not ideal for putting into a crimping tool, but in this case, well, I've never had a problem with it. And doing the pull test, and incidentally with the PA09 I did the pull test, I stuck it into a connector and then pulled it out, and the little ratchet tab actually physically bent back before it released. It didn't just pull, the wire didn't just pull out, so they're a good result. However, I've found that these grip on solidly, and if you look through a magnifying glass, it actually seems to bite into the actual core of the copper. It looks a bit like this. If this was the looking end onto the solid core, it kind of bites into it like that. So it does make a decent connection, and I've never had a problem with them. And I've had some lights like this running for quite some time, like 8 years, some of them. So they've been pretty good. Not that they get a lot of strain and moving about. The circuit I'm going to be using, I'm not really sure. I could go for a resistive dropper because this is purely decorative. It doesn't have to be too fancy. It's not trying to light the room. So I could go for a capacitive dropper or a resistive dropper. I'm thinking of going capacitive dropper and using either an X2 capacitor, which is a sort of good quality special capacitor, or just basically the equivalent but without the little epoxy box. And this is just a generic 400 volt capacitor, which would work just as well. I'm also thinking of using smoothing. Let's go over the circuit. It's not that complex. Let's zoom in a little bit. Some of you may notice the sound is very, very different. The picture may also be different. It's a different recording device, and this time, and I don't normally do this, I'm actually recording in stereo. I'm not sure this is a good thing. You can let me know what you think. The main advantage for me of stereo is that Dolby is not going to put my audio out to the middle bass bin, because it tends to interpret my bassy voice, and the fact that I normally record the videos in mono, it tends to interpret that as a bass channel and then stick it out to a middle speaker, which means that if you've ever looked at some of my videos in the past and they've got no audio at all, that's because if you listened on a different device, you'd hear the audio. But anything with Dolby surround sound sometimes just basically terminates the audio in my videos by putting it out to a missing speaker. It's very odd. So what I'm going to do here, I'm going to have an Inrush limiting current, Inrush current limiting resistor of quite a high value, because this is all going to operate at low current. It's going to be about 470 ohms. It's going to go into a discrete rectifier made of 1N4 007 diodes. It's going to either have a resistive limiter, in which case both these resistors, I'd put a resistor in each leg, or maybe a couple in each leg, and it would be quite a high value, so it would be quite a low current, because it would be dissipating any excess across these resistors, and they'd get warm, and you'd want to keep them well within the rating. Or for extra brightness, I could go for a 100 nano or 220 nanofarad capacitor with a 1 megohm discharge resistor across it to avoid little tingles, because I plan on putting it into something like a lamp base like this. And the output will have a electrolytic capacitor that I've robbed out a Chinese lamp kit, 400 volt, 4.7 megafarad to get rid of flicker. And then it will have a couple of 470 ohm resistors beyond that. And the reason for those resistors is that after that, it's just a solid chain of LEDs in series. Each tip of the plant is going to be an LED. And if I do what I normally do and I end up hot swapping LEDs, which is not recommended because, you know, there is a risk of a slight shock off them, then, because it is mains voltage effectively, then what happens if you unplug an LED, the voltage across this capacitor rises up to about the peak mains voltage, which in our case will be about 330 volts. Because that's 240 volts AC times about 1.41. That's the peak voltage the capacitor will charge to, because it's at the RMS value is the sine wave, but that's the average over the whole sine. The peak is a lot higher than the average. So for 240, it's closer to 350-ish. So I've got that capacitor, and if you unplug the LEDs, normally the LED voltage would have been down at, say, if I use 30 LEDs, 3 volts each, 90 volts. So it would normally pull the voltage in that capacitor down to 90 volts because the current's limited by this side. But if you unplug it, that shoots up to 330 volts. Then when you plug an LED in, it immediately discharges the difference in voltage from that capacitor through the LEDs, and it can actually pop the LEDs, particularly the colour-changing ones. By adding a couple of 470 ohm resistors in series, they're not going to dissipate too much power, but they are going to limit that current spike down to just a few hundred milliamps, and it means it's going to protect the LEDs. That is the idea. This is a rough spatial representation of what I'm going to do. I'm going to hardwire it. But the first thing is to actually terminate all these wires. So what I've done here is I've stripped loads of bit of solid core wire, and I've started sticking crimps on them, and rather than punish you by making you watch me put crimps, basically about 80 crimps on, I'll just pause the video and then we can continue once I've done that. Much crimping later, and I've got all my ends, and it's worth mentioning, if I didn't mention it before, the length of these wires, these solid core wires, is approximately 12 inches, 300 millimeters, 30 centimeters, and that's just at a good length, because ultimately these are going to be sort of halved in length. They're going to be folded, so the sort of tendrils of the LEDs in the end are going to be roughly half that, 6 inches, 150 millimeters roughly, minus whatever is in the base. I've got the socket part of the connector here, and on the negative side of it, I tend to use the pin 1 as a positive on these connectors. So I mark the negative with a bit of sharp in the end. And the reason for that is that when you're putting LEDs in afterwards, if you get them in the wrong way round, those LEDs will usually be destroyed because the open circuit across them will be quite high, open circuit voltage. Interesting things to note. These generic eBay ones are very white. The ones I get from Rapid Electronics are sort of beigey, creamy white. I've also noticed something on it that I've never spotted before. It's got a number, 2510, and that does relate to the KF2510, so that must be a generic reference to these connectors. This also has 2510. It, interestingly, has the 1 marked on the positive side, which is useful. I wonder why this brand didn't do that, but it doesn't matter. So I'll show you what I'm going to do here. I'm going to start with one of these tails, and I'm going to stick it into the positive connection, which is pin 1. Click it in, and I'm going to, the next wire, and this is where they all hook on each other, I'm going to plug it into the negative going output from that, the negative connection. Make sure it snaps in. And then I'm going to go from this one to the positive, and I'm just going to keep doing that, basically creating a string of continuous lights all wired in series, loads of sockets. And when I say lights, what I mean by that is that by the time I've got a few of these in, connectors that I have not over crimped, because I found these were a wee bit harder to slide into the crimping tool. I've got spares. By the time they're all in, the reason I'm using little sockets is so that the LEDs, I can actually just shove them directly into the end instead of a plug. And they'll make connections to those springy pins inside, and it just means that you can just fit LEDs in as you desire, which is nice because it means that if you make a display of LEDs, you get a nice sprig of these sort of LED sort of tendrils, if you will. And it means that if an LED fails or gets dim or you want to change the colour, you can just unplug the LED and you can plug a new one in. It reminds me a lot of the original Chinese night lights that had the little mushrooms, and they had a couple of white LEDs and a colour changing one, but the nice thing about the original ones was that you could unplug the LEDs from them and you could put new ones in, but they changed that. They made it so they're permanently on. I think that might partly have been because people were pulling the toadstools off with the LED, and if they put the LED in the wrong way around, it failed. Or maybe it was a safety thing, or maybe it was a cost thing. I'm not sure why they did that. This is absolutely the inspiration for me using foliage and LEDs together to create a sort of plant effect. So now I'm going to keep munching away with these. I'm going to keep looping them end to end, and once I've finished doing that, I shall return. Much threading of crimps later, and I've lined these all up so that effectively, and I just used 2 of the standard crimp connections as the positive and negative. It's effectively going zigzagging backwards and forwards between the ends now. And I've got, it ended up about 21 sockets on one side and 22 on the other for a total of 43. Now, I'm going to actually fan them out from the middle. I'm going to put a cable tie around this in the middle. I've got the option here that if I was to put this cable tie slightly to one side, it means that you'd get different layers by the time I'm finished of the LEDs. But I've found in the past that putting it dead center is absolutely fine. So what I'm going to do now, I'm going to make sure that's tight, and then I'm going to just wheedle out pairs of wires with the connector like this. And this is where it's really going to test where these crimps stay in the connector, because I'm going to twist them like this. And by twisting them like this, it becomes effectively a stem that will have the LED in the end. And it's quite springy, it's quite a time-consuming job to twist them. You also may have to slightly shuffle them a bit because they may have passed through each other in the process of bundling them up like this. But this is basically what I'm going to do on both sides. And once I've finished, I shall return and we shall build the power supply that's going to power this arrangement. And then we'll stuff it with LEDs and then work out what sort of foliage we're going to be using and what sort of base we're going to be putting it in. It's all made up, like the best projects are. So I shall keep twisting these wires like this so you can see the whole effect that what we're getting here is basically a sprig of stems that will have the LEDs in the end, but they're all wired in series. So we'll continue doing this and I'll be back shortly. It's decision time. I've made the foliage cluster up with the sockets interspersed. I've not mixed them through the foliage yet because I'll only do that once it's actually into the base and once it's all resined in. So now I've got to decide what sort of power supply I want. Now I've got the option here. I could do a super safe but low intensity one. I could have one where live and neutral, although it's going to probably be in this base. So live and neutral is a bit of a moot point because it can go in round either way. But one approach would be to use 1 or 2 resistors in series with a bridge rectifier, full bridge rectifier, AC in plus minus. And then the output, I'm going to use an electrolytic capacitor which I've robbed from a component kit for a Chinese LED lamp kit. 4.7 megafarad, 400 volts. It doesn't have to be that high because the current of the circuit is going to be very low. But that capacitor would go across the output just to get rid of flicker. It's not needed, but there could be a slight peripheral vision flicker without it. Then I would put a couple of resistors. I mentioned those resistors earlier on, the sort of Inrush limiting, and then it would go out to the LEDs. The other option I've got, and the one I'm biasing to, because the problem with using resistors, though it's super safe because you could put a high value of resistor, and it means if someone does come in contact with metal work while holding grounded metal, other metal work, it reduces the risk of a shock. But having said that, this is my own personal use. I'm not too bothered by such things. It's going to be out of reach. You could make a safe version of this where every single LED socket just simply had a resistor in series with it, and that could then run off a USB power supply and it'd be ultra safe. But I'm not going to do that. I'm wanting one that just goes into a lamp holder and it looks like a sprig of foliage with LEDs in it. So the approach I'm probably going to take is, let's get rid of that one. The approach I'm probably going to take is to have live, neutral, or they could be in the other order, a capacitor, and I'm going to choose 220 nanofarad for extra brightness. I'm putting a discharge resistor across that. In reality, I'm putting 2 because each is rated about 250 volts DC, so it's better to have that. You know, it's a little bit of extra safety, and I've already made that assembly here. I've got the capacitor, and I'm using the standard Chinese, you know, capacitive dropper type capacitor, although sourced in the UK from Rapid Electronics. And I've got a couple of 470k resistors across that, times 2, which is going to give roughly best part of 1 megohm. It just means that when you unplug it, you can't get a tingle off the pins if it's got a charge. That is then going to the bridge rectifier. And to limit the inrush current and act as a kind of fuse, I'm also going to use another component out that kit, a 10 ohm resistor. I was going to use a higher value resistor, but 10 ohms, fine. And this is a metal film resistor, so it's going to be a fusible resistor as well. So here's the bridge rectifier, which I'm going to build with discrete diodes, AC in, plus minus, and the rest is going to be the same. It's basically going to be those two resistors, and it's going to be that capacitor just for smoothing. Technically speaking, it would have been nicer to use a higher value resistor than the 10 ohm because it would reduce the inrush current and protect that capacitor there. But it doesn't really matter. I've had plenty of these running for a while without any problems. So these are going to be 470 ohms. 470 ohms. That's going to be 400 volt, although it won't really go near that unless one of the LEDs is unplugged, the circuit is unplugged. The circuit is broken, so to speak. Plus, minus. And that's going to be 4.7 microfarad, just because that's a really standard Chinese value. So that is the circuit that I'm going to be using. Now to make this, I'm going to hardwire it. There's not going to be a circuit board. So the bridge rectifier itself, the standard schematic for a bridge rectifier is this. It's the 4 DATs, it's the diodes, and the diodes all point towards the positive. That's the easiest way to remember how the diodes are configured in a bridge rectifier. They point away from the negative to the positive. And the whole point of a bridge rectifier is that this is AC, this is AC. If this side's positive and this side's negative, then the positive will effectively find a path through this diode, and the negative will find a path through that diode. If the polarity changes and this becomes negative and that becomes positive on the other half of the sine wave, then the positive will find a way through this diode and the negative will find a way through this diode. So it means that no matter the polarity, positive is always going to end up going to positive and negative is always going to end up going to negative, keeping it in simple terms. So to make this rectifier, all I'm going to actually do is fabricate it from discrete diodes. I'm going to use 1N4007s, 1N4007, which is a 1000 volt, not needed 1000 volt, it's just a standard diode, but it's a 1 amp diode. Doesn't even need to be 1 amp, but it's such a generic common diode. You'll recognize these type of diodes, you see them everywhere. So if this is positive, I'm going to twist the leads like this and then solder them. So that's going to be AC, AC, minus, that's going to be positive. So the band is going to be pointing towards the positive in all instances. So from the negative to the positive, the band is always going to go in that direction. There's a little band on the end of the diode, a silver band on the end of the black diode. And then the AC connects to the two connections that have a band and a non-band, just because that's how it works out. Let us start making this. This is when it would be quite handy to zoom up a bit closer. Let's zoom up a bit closer. Let's take the intensity lock off and brighten that up. Zoom in a little bit. And we shall start by twisting two diodes with the positive bands pointing to the end. So this is effectively going to be the positive connection. So I'm going to twist those diodes like that. And I'm going to get another two diodes and I'm going to twist the non-band end, the negative connection ultimately. And I'm angling these slightly as I do this because they're going to form a little square, just because it's going to more or less match the circuit symbol, the schematic. So I've twisted those like that. And now I'm going to twist them with the other diodes like this. So these are going to be the AC connections. I should do my best to stay in shot. I think I'm staying in shot. Things are different audio and visually wise. I'm trying a bit of audio processing software and it's a different camera. Still in the Moto range because I like the Moto range. They do get the cameras right, usually. And if a recipe works, don't mess with it. So this is the rectifier. I'm now going to solder the ends by just basically flowing some solder in like this. And then it starts getting very hot very quickly. Just at the point of the junction of the diodes, leads. Has that cooled down enough yet? Yes, it has. And that just leaves one connection to solder. And that is a classic bridge rectifier, a full bridge rectifier. It's an ugly rectifier, but you know what? It's going to rectify, and that's kind of all I want. Now that these are soldered, I can crop them fairly close without going too close, and they'll kind of hold their shape even when there's sort of more stuff is soldered onto them. Okie dokie. Right. So first components I'm going to solder on are the two 47 ohm output resistors. They're going to point up the way, I think, up towards the sprig of foliage. So I may just actually solder them side on, and that just then lets me fold them up. I shall do that. So I shall pre-tin. I've misplaced the solder. There's the solder. I shall pre-tin this. And put a little blob of solder on it. And then I can flow the others together. I shall add a bit of flux as well, just because it helps the solder flow together. I'd like to actually leave a blob on that, but it's not leaving a blob. That's all right. I shall do the other one at the same time. So these are two 470 ohm resistors that are going to be in series with the LEDs. One is going to the positive of the rectifier and one is going to the negative. Right, so let's get the flux. Where's my flux pen? And we'll put a wee tiny femtopol of flux on these. And that just means that when I'm re-solder onto the rectifier, it's going to flow better. Regular viewers of the channel will be totally getting deja vu because I've done this project style before. Perhaps not in quite a flamboyant floral style. It's just the mood I'm in to do something like this. So now I'm going to reflow those together. So that's one connection done, and now I shall get the other connection, and this will go to the negative end with the bands all pointing away from it. Wish I had a wee touch more flux, but that's alright, it's fine. I prefer it when it makes that slight hiss of the flux evaporating, but that is absolutely fine. There's nothing wrong with that. Now on the AC input, I'm going to have the capacitor here, and this is where I have to think, oh, you know what else, you know what, they're going to fall off because I should have soldered the capacitor on before I did that. That's alright, we can improvise, we can make this work. I can put the capacitor up like this, make sure I get the capacitor polarity the right way around, otherwise it won't end well. So I'm going to fold the leads sideways in this. Just grip them so I don't damage them and don't pull them out of the capacitor body. And the long lead, which is a positive, the negative is marked with this sort of the band on the body here. So the negative will go to the negative, which is at that side. And the positive will go to the positive, which is at this side. And I'm just going to wrap them round actually. I'm going to get roughly central, wrap it round like that, wrap it round the existing resistor leads, and that should hold them in place. It's a bit messy, but you know what? It's going to work. And then I'll reflow those, and this is where those resistors just instantly drop off. I'm just going to double check the polarity of the capacitor first, because if I get that wrong, it's going to be noisy. Those electrolytic capacitors tend to vent when they get connected up in reverse polarity, but in this instance the current would be limited by the dropper capacitor, which basically lets a small portion of current through on each half of the sine wave. Everything is so far holding together. Oh, that resistor's trying to escape, but that's okay. It almost escaped, but it didn't escape. It's fine, it's staying put. Now, on one of the AC inputs, I want this resistor. Note that this resistor, despite the fact it's in the vicinity of the capacitor there, this resistor will not get very hot because it's only acting as a sort of fuse. The current flowing through it is minute. And on the other side, I'm going to have the capacitor, which can go around anyway because it's a non-polarized capacitor. So let's solder the capacitor on first, I think. And I'll make this as compact as possible, but there is a limit. I'd need to save as much space in the case here as possible. Where is the solder? Right, let's get... I'm actually holding a square capacitor against a round capacitor, which isn't terribly easy. That's worked. Okay, and I can crop that lead off. Now I'm wanting the resistor lead to be fairly similarly positioned, but there's a bit of leeway. The resistor is fairly flexible where it can go, really. So I shall put it here. I shall actually just wrap one wrap of that round there, just because it's going to result in a much better mechanical connection, and keep it in place while I solder. This is famous last words because it will instantly drop off as soon as I solder it now. Let's give it a go. That's good enough. It can bend back into position. That is our power supply. We've got two little resistors coming up to connect to the LED. And we've got this that's going to ultimately go down into the base if this fits. Is this going to fit? If this fits perfectly, it's going to fit. See how this is metal here? I want the capacitor and stuff to go down beyond that. I want to go down the middle like that and keep everything away from that metal for obvious reasons, and have those connections come out the bottom so that they can be folded over and then these rivets can be put in. And you know what? That has worked out pretty damn perfect. Right, so now I want to actually consider putting the foliage in. This is going to be a bit of a juggle because I'm going to have to kind of seal the top of this. I don't want to pour resin right down into the base here because A, it makes it re-enterable for repairs, but also I have to consider that the bottom of the capacitor here needs to be able to vent out if something goes horribly wrong. So I may have to improvise things. Okay, right, let's start by getting the foliage leads. I've marked one of these leads as black down here. I'm going to bring that mark up here all the way along here. If you're getting a good picture and you're very observant, you'll see that I've already damaged my floral arrangement here because initially I thought it'd be quite nice building the whole lot, including this if it had fitted, into a plastic tube like this, which would have been a tight fit but possible. And I tried it for size over the end of the wires here, and it was quite tight, so I just wiggled it, and the sharp edge actually scraped the insulation off some of the wires. It's not really a significant issue because it's a current limited supply, but it annoyed me, as such things would do. So let's crop these to a size and then splay them out and connect them to those resistors. This will do. It's going to do now. Let's bring in my stripper. I'm going to strip one of them with my classic Junior stripper. And then just for equality here of strippers, let's bring in the other little dinky stripper. This one is so annoying, it's quite cheap. If you unlock it and it pings open, the spring in the middle just flies across the room. It's quite annoying. But this one also works, so it's fine. Let's just nudge that down a little tad more. Excellent. And make sure I lock that off properly so I don't have to go hunting for the spring. So I'm going to splay these wires out. They are going to connect to the resistors here. Okay, I shall make this up as I go. It would probably be worth noting, right, that's the negative at that side, and this is the positive here. Rightio, I shall crop the leads down a bit and put these leads directly onto those resistors. Is this a good idea? I'm always thinking I could have got this so much closer up. No, that's actually pretty good, actually. Right, the negative I shall twist around the negative resistor. Now I wish I'd left that resistor lead longer, but I'm just making this up as I go. You may have noticed that. It's quite late at night, but I'm not really in a rush to get to bed at the moment. It's the weekend. It's time to relax and make stuff. The next step before I actually put this into the base is to test it. And that means I'm going to have to go and grab some LEDs and put them onto into the sockets and then plug it into the mains and see if all my work gets undone with a loud bang. It doesn't always happen. I mean, it does occasionally happen, but I would say as I get older, it happens less. But you just never know. Okay, right. That means I now have to test this. So I'm going to double check. That one had the black mark in it, and it goes to the negative connections. This one has the positive and goes to the positive connections. If anything, those little resistors are maybe a bit too flimsy. But here is the whole module. Ready to go in. It's quite compact. That is in the vicinity of one of those damaged wire bits, so let's rotate that so it's not. And those resistors, again, they're not going to get very hot. Right, I'm going to get some LEDs and I'm going to put them into this and we'll give it a go before I box it up, because otherwise, you know, it would be disaster otherwise. Ah yes, the simple choice of LED colours. I was going to go for warm white, and then I thought, what about these sort of flat top, well not flat top, the straw hat white LEDs, warm white LEDs. And then I thought that since I'm filming this on the 22nd of December, it makes sense to go for the Christmas theme by putting in red LEDs. I have to say that, I suppose you could say it's part of the flower, the white base. It might have been nice to actually have coloured that. But anyway, I have put all the LEDs in, hopefully in the right direction. Let's get that down out the way. Let's bring in the hoppy and let's give this a test. So I'm going to jam the leads and then hold it up. So I'm going to put the capacitive dropper in to the live. I'm going to put the resistor into the negative. Is this going to work, or is it just going to fail apocalyptically? Oh. It's kind of not worked. That's exciting. Okay, have I got the Pliers the wrong way around? Have I broken a connection, or is it just not make a connection to the base? Right. Okay, that's a bit scary. Oh. There's a possibility, because the way this works, that it didn't make a good connection. So just as a precaution, I'll bring in the quick test. There is a possibility that I've screwed up and there is something making a bad connection in the LEDs here. And there's also a fully charged capacitor, charged potentially up to 300 volts in here now, because I forgot a discharge resistor. Okay, I'll keep that in mind. Let us pop this in here. There's a possibility that there is an open circuit. There's a LED missing, maybe. I don't think there's an LED missing. Or that one LED, it's doubtful that it would have an effect, it was the wrong way around. Let's close this over, let's plug this in. Let's plug the correct lead in. Let's untie this knot in the hoppy lead, not the hoppy, but the quick test lead. That is not lighting. Excellent. Let's probe with a meter and see what voltage I'm getting across the string of LEDs. So I'll put this up to the 1000 volt range for this. And then precariously probe there and there. Oh, I'm getting 337 volts across the LEDs, but the LEDs are not lighting. So I may have missed an LED. I shall have a wee look at that. I shall actually discharge that. That sounds like a great idea, doesn't it? Just out of interest, how long would it take to discharge just the meter? Probably quite a long time, because, yeah, that would take a while. Yeah, that would take a very long time. Okay, right. I'm going to probe about. I'm not sure how long it will take, so I'll just pause momentarily while I do this. Oh, that was super annoying. That took so long to find the fault, because these little terminals, they seem to be a bit different from the other ones that I use. slight tolerance difference, and it means that the LEDs, some of them were not making a connection properly. I weeded out the ones that were duff, finally found them, but because they're scattered randomly, you can't just trace it along like you could with a Christmas tree with all the lights in a string. It was actually quite hard finding the problematic ones. However, it is fixed, and the power consumption, it's passing 16 milliamps, but keep in mind there is an element of this charge the capacitor. That's not necessarily the current going through the LEDs. 245 volts, it's using 1.6 watts, which is perfectly fine. The 0.4 power factor is typically what you'd expect of a circuit like this, capacitive dropper with a smoothing capacitor. So the next thing is to pot it into the base. Where is the base? Here it is. So I'm going to do that now, and I shall, let's proceed with that. I'm going to go and get the hot melt glue gun. Time for the hot melt. I've poked little bits of foam down into the area just down there, just to try and stop the hot melt flowing down into the electronics below. And because it's fairly viscous and will cool down quite quickly, it should basically form a sort of layer in here and secure this to the side. And then after I've done this, I'll probably use 2-part resin just to take it up to the top, because that has a more better flowing ability to actually flow in amongst the sort of wires and sort of fill in that area. So I'll start off by doing that. The foam, by the way, you might think, well, isn't that dangerous because it's combustible? Well, hell yeah. It just seems the best option. There's not much heat down the base anyway because of the type of circuitry. Okay, it could malfunction horribly. But hopefully the hot melt glue sticker's just run out. Hopefully the protective components will do their job, and to be honest, it's not a high risk. The fitting it's going in is probably going to be metal anyway. Oh, you know what's happened? Oh, that was unexpected in a way. The foam that I put down there has just immediately shriveled up with the heat from the glue gun, and the glue is now going into the base. Right, excellent. Well, I'll just hold off momentarily then. One day later, because I kind of finished last night by just basically filling the whole thing up with hot melt glue. It's fine, it's nice and solid. It's really robust because it is full of that. I don't know how much went down into the base where I was trying to keep it out of, but it doesn't matter. I also found out, with a bit of experimentation and measurement, why these contacts weren't making such a good connection with the LEDs. And the answer is that the little folded round contact, the springy contact end, is narrower than the ones I normally use. So whereas on the one I normally use, it pretty much fills up the whole terminal. On the other one, these ones, instead of filling up that whole space, the little contact at the end is narrower. It's not much. In the ones I normally use, it's 1.25mm. This one, it's about 20% less. It's 1mm, but it's just enough that if an LED is put in and it just goes in at an angle, it can actually go down the side. But you'd still wonder why didn't it make a connection? Because it's full of metal, but it didn't. So keep in mind that this version of the tree is mains voltage, and by mains voltage I mean that the little tangs that hold the contacts in are effectively, they don't stick out, but they're close to touch. They're effectively connected to the mains via a 10 ohm resistor and a diodes, and that's it. So it's not something you'd really want to leave around. And likewise, when you pull a resistor, an LED out, just say, keep in mind that as you're putting it in and out, those connections are live at mains voltage if you were to make one using this technique. However, there's another way you can make it. You can do it as a USB version, and I've shown that in other videos. You get the same arrangement here, but instead of having one lead looping around all these connectors, you have a pair of leads, one per side of the connector, and you solder in a 220 ohm resistor and then put some sleeving over it. The soldering of the resistors is the most critical bit. I would recommend a bit of flux, extra flux for that, particularly if you're going to tin the leads in advance. I'd also recommend a helping hand to help with that. One of these little things that has the clips that hold things in place, and a base. And once you've done that, you can take all the ends, and the more the merrier, to be honest. But I found in the past when I tried making larger versions of this that if you twisted all the ends together into one big clump, it was very hard to solder. So I recommend limiting it to about 5 per clump, twist them together, solder that each group of 5, and then take another bit of wire and put a couple of loops around it, and then onto the next one, a couple of loops, and then solder those. And then this wire will link them all together. And they can all still be mushed into the same space, but it just makes it a lot easier to get that connection to a lot of ends. And one of the other advantages of using the USB power supply to power this, and all you need for the cable is just to cut an existing USB lead, just cut the micro USB connector off and leave the original end on. And then just get out the positive and negative wires. The other advantage of that is that each LED is independent. So even when you take an LED out of this one, it's actually going to keep all the other ones will stay lit. So if you do have a bad connection in one of the holders, it will it won't really affect others. Just that one LED will go out, and then you can wiggle and reinsert it to actually until it makes connection. That is huge advantages, because this is definitely not one you want kids poking around with, or even adults poking around with if they think, oh, that's lovely, and they run their fingers through it. It could be called the Krampus tree. That would be seasonal. I mean, I chose the red LEDs and the green because right while I'm making this, it's Christmas in about 3 days at this point in time that I'm making this. And I just thought the red and the green would be a nice Christmassy theme. But it's almost, in a way, a Krampus tree that imparts small gifts to impertinent children who fondle with the branches by literally tossing them into the air like a ragdoll. That's what you call a Christmas gift for bad boys and girls. But there we go. Now, is there anything else worth saying? Yes, there is. You could use the little... what do they call these again? I can never remember the name of these connectors. It's such a... Particularly when I start recording. Right, give me a second. It's the Arduino type connector. No, I've completely forgotten the name of that again. I don't use them much. DuPont connector, that's the one. I bet you're all shouting DuPont. But you could use the 2-pole DuPont, but keep in mind that it doesn't really... You'd have to crop the LED leads probably equal lengths for that, and the length they can go in is quite critical into it. It's also, I find these little crimps quite hard, even with the Engineer PA09. I find these are very prone to sticking in the actual connector. Maybe a little touch of oil would help there with getting them out. But there we go, that's it. I shall show you the end result. I shall just basically turn the light off, and if I take exposure off, this is just going to go really swamped out, isn't it? Yeah, that's not bad. That's a fairly accurate representation of what it looks like with the green sort of foliage there just highlighted by the red points of light. It looks pretty good. I like it. It's a good result, and if you stick it in a sort of ceiling chandelier type fitting, well, I say chandelier, one of those things with the multiple sort of stems, the lamp on each end, it kind of looks weird, but really nice. I may change these for warm white LEDs. I may change them for colour changing LEDs, or the sparkly straw hat type white LEDs with the visible endpoint. It would be nice to put the Christmas light style LEDs in, the ones that have the convex lens at the top, the little dimple in the end that puts the light out sideways, but it's very hard finding a decent source of cheap LEDs that style, even though there's some mass-produced the Christmas light industry. You can find them on eBay, but they're just not, they're not what you call cost-effective. Someone is just basically, they've bought some and they're selling them at quite a high price. It's also worth mentioning that the cheapy Christmas LEDs don't last terribly long. They tend to lose intensity very quickly over the course of literally a year of operation. But the nice thing about this light is that you can just change the LEDs. You can just pop new LEDs in if you wish. Oh, and you can shake it and they vibrate. Boing. Another thought that I had was that if you, instead of putting the foliage into this, you left a recess down the middle, like a bit of sleeving or a little plastic tube, then you could put in different foliage and just adapt it to suit whatever you wanted with different colours of LEDs. It's actually very versatile. But yeah, it's a good result. I like that. It's not the first I've made, but I do like that a lot. And although everything went wrong during the making of it, it has worked out absolutely fine and it looks really, really good.